In Module 18H, we're going to start talking about solubility again. We've talked about solubility, but that was back in first semester when we just had you memorize basic solubility rules of yes, this is soluble, or no, this is not. The truth is it's not that simple, and so nothing's ever that simple. So we're going to start actually examining within this rules what we taught you before. So you should go ahead and review your solubility rules for ionic compounds in water. That will help in this section. From this section, you should be able to write the equilibrium equation for a saturated solution of what we call sparingly soluble salts, a sparingly soluble ionic compound, and define the value of KSP for that salt. Calculate KSP for a salt from the salt solubility data, use the value of KSP to determine the solubility of a substance in pure water, and use KSP to determine the solubility in the presence of a common ion. So first, just as a quick review, here's your solubility rules. You can go ahead and look through those as you'd like. Hopefully remember them, but these are the base solubility rules we taught you guys. That doesn't mean that they're the only rules, it just means they're the rules we taught you in Chem 1. We're going to use KSP. SP stands for solubility product, and KSP equilibria is used to describe sparingly soluble salts. Basically, the truth is when we say things don't dissolve or are insoluble, that's not quite the truth. Really, a small amount actually does dissolve, but it's a small amount, so we say it's insoluble. In this section, we're going to start examining how much actually dissolves. So again, KSP is just equilibria showing you how much is actually going to dissolve, SP standing for solubility product. So solubility itself. When discussing ionic compounds, the word insoluble, as it is used with the solubility rules, is, strictly speaking, not a correct term. Why? Because a small amount actually does dissolve. How much? Depends on the compound. Solubility is defined as the amount of solute that will dissolve in a given amount of solution at a particular temperature. Why do we specify solution here and not solute? Or solvent, I mean. Solution takes into account everything in solution. We've learned when we talk about equilibria that we can have things like the common ion effect, Le Chatelier's principle. We're going to talk about the common ion effect again in this section. But let's say I'm trying to dissolve some lead-2 chloride, PbCl2. This is slightly soluble. A little bit will dissolve, but not very much. The way this works is this solid is going to form some lead-2 plus and some chloride ions. But what if I have chloride ions already in solution? What if this solution has some KCl in it? Then I've increased the concentration here. What's going to happen? Less is going to dissolve, right? So we say the solubility is the amount of solute that will dissolve in a given amount of solution at a particular temperature because it depends on everything that's present, not just the solvent. Lead-2 chloride, a little bit in a certain amount will dissolve in water, but less will dissolve in a KCl solution of water. Molar solubility is defined as the number of moles of solute that will dissolve in 1 liter of solution. This is your molarity of the dissolved solute in a saturated solution. Other terms which are used in place of insoluble are slightly soluble or sparingly soluble. Those are other things you're going to see. Because they're slightly more correct. We say insoluble, but the truth is a little bit will dissolve. So, when a sparingly soluble compound such as silver chloride is placed in water, how can you tell the solution is saturated? We talked about saturated before. Saturated means no more will actually dissolve. The most that will dissolve is already dissolved. But how do we know it's saturated? There's a quick way to tell, truthfully. You've got a beaker here. And you put silver chloride in here. If you've got some solid sitting at the bottom, it's saturated. If you have some undissolved solid or solute present. Of course, you can calculate it as well. You can calculate Q and compare Q to K and see is the solution saturated or not. But if you're actually in a lab and you need to make a saturated solution, my students need to do this in organic a lot. Our TAs need to make saturated solutions of sodium chloride in organic a lot. It's common extraction we use. And the way they make it is they just dump a bunch of salt into water until it doesn't dissolve anymore. Then you know you have a saturated solution. So reality versus conceptual. Lecture is going to tell you to go ahead and calculate that Q value and compare Q to K, see how much you can dissolve until it's just saturated. Reality is we're probably not going to calculate it. We're probably just going to go dump some in there until we have some solid left over in the bottom, and then we know it's saturated. What is the chemical description, i.e. the reaction in KEQ, that is used to describe a saturated solution of silver chloride? Silver chloride in equilibrium with silver ions and chloride ions. And the KEQ, we specifically say KSP for solubility product. It's still products over reactants. In this case, AgCl plus, Cl minus. We don't have a denominator because it's a solid on the reactant side. And this happens to be equal to 1.77 times 10 to the minus 10th. These, again, are values that you would be given if you needed them on an assessment. We do need to talk briefly about the common ion effect. Remember that the common ion effect is in play. So, what do I mean by the common ion effect? The presence of common ion represses the ionization of a weak electrolyte. It makes X even smaller. This affects our solubility. The common ion effect is application of Le Chatelier's principle. And remember, if you have a strong acid or strong base, these can also be a common ion. I need you to be actively thinking about that when we're doing these systems, because they can affect the solubility of things. So, like I said, if I'm trying to dissolve silver chloride, if I added HCl to this, if I added sodium chloride to this, if I added silver nitrate to this, all of these are soluble, which means they split into their individual ions. But they're all going to create either more silver ions or chloride ions in solution, leading to less solubility of the silver chloride. And you need to be actively thinking about that when you're doing these examples, because they will affect our solubility. Write the KSP equations for the sparingly soluble salts below. If I have lead 2 chloride, if this is a solid, I know by rules this should be insoluble. What it really means is a little bit breaks up into lead 2 plus and 2 moles of chloride ions. The KSP here is equal to Pb2 plus Cl minus squared. Remember that the coefficients become the exponents. We haven't had to deal with that for pretty much since the equilibrium chapter, but that's back. And this equals 1.17 times 10 to the minus 5. Nickel carbonate, also sparingly soluble salt, forms nickel 2 plus ions and carbonate ions. KSP here, nickel 2 plus and carbonate, and this is equal to 1.42 times 10 to the minus 7. Again, how do I know these values? Because I looked them up. I will give them to you when you need them on assessments. Silver chromate, solid. Silver is rarely soluble. Silver nitrate's the only one I know of off the top of my head that likes to be soluble. It gives me 2 moles of silver ions and 1 mole of chromate ions. The KSP here equal to Ag plus quantity squared, don't forget that 2 out in front, times CrO4 2 minus. and this is equal to 1.12 times 10 to the minus 12. And Hg2CO3, solid in equilibrium with Hg2 2 plus. You have to recognize that polyatomic here. Plus CO3 2 minus. And KSP here. Hg2 2 plus. CO3 2 minus. 3.6 times 10 to the minus 17. Now, if you look at these numbers, you should be able to rank the solubility from most soluble to least soluble. Or let's say least soluble, most soluble. By the numbers. 1.17 times 10 negative 5, 1.42 times 10 negative 7, 1.12 times 10 negative 12, and 3.6 times 10 negative 17. 3.6 times 10 to the minus 17 is the least soluble. It's the smallest number, meaning the smallest amount has actually dissociated. 1.17 times 10 to the minus 5 is the most soluble. 1.12 times 10 to the minus 12, and 1.42 times 10 to the minus 7. So you should be able to tell me which one is most likely to dissolve, which one is not, based on their KSP values as well. Okay, learning objective. Be able to use solubility data to determine the KSP for a soluble salt. The solubility of antimony sulfide, Sp2S3, is 0.00175 grams per liter. What is the KSP for this salt? The process you're going to follow. Number 1, convert your solubility to molar solubility. So molarity or moles per liter. Our solubility is 0.00175 grams per liter. I want this in moles per liter. 1 mole of Sp2S3 weighs 339.68 grams. This gives me 5.16 times 10 to the minus 6 molar. And we're going to call this S for solubility. Two, set up an ice table, plug your equilibrium values into the KEQ expression. So I've got Sp2O3, or Sp2S3, I apologize, Sp2S3, and that is a solid in equilibrium with 2 moles of Sp3 plus and 3 moles of S2 minus. I don't care about the solid. Doesn't matter to me. Doesn't do anything. I don't have any Sp3 2 plus or S2 minus present to start. But my molar solubility tells me that S of this, I'm going to say minus S here, even though I don't really care what's actually here, is going to produce 2S here and 3S here. If you're not comfortable with the S, use X. We only use S because it represents solubility. Okay, so it's just like we've done with rice charts before using X, but this time we're just using the letter S for solubility. I know some students have a hard time with the letter S because it looks like a 5. Use X if you would feel like it. I don't care. At equilibrium, 2S and 3S. Set up your KSP expression. KSP is equal to SB3 plus squared times S2 minus cubed. Plug in your values into that. And so this equals 2S quantity squared times 3S quantity cubed. 2S squared is the same as 4S squared. 3S cubed is the same as 27S cubed. Now you multiply those two things together. 4 times 27 is 108, S to the 5th. If you're uncomfortable with how I got to this point, you can go ahead and plug your values in under S right above that. I don't care. I like to simplify these down as much as possible before I plug numbers in because I'm more likely to make a mistake in my calculator if I don't. So I've got 105 or 108 S to the 5th. But what is S? S is my solubility, my molar solubility. Which I determined already. KSP is equal to 108 times 5.16 times 10 to the minus 6th, quantity to the 5th. My KSP is equal to 3.91 times 10 to the minus 25. Not very soluble. But this is a way for you to be able to use solubility data to determine the KSP for a soluble salt. If you know how much it's going to dissolve, if you know the solubility of it, you can tell me the KSP. Okay, next one. The learning objective here is to be able to determine the molar solubility of a substance in pure water. So I want to know what is the molar solubility of AgBr in pure water. The KSP is 5.0 times 10 to the minus 13. Go ahead and set up your rice chart. AgBr, solid, in equilibrium with Ag plus aqueous plus Br minus aqueous. I don't really care. I'm just going to write minus S under the AgBr to show where the S is coming from. I don't have any Ag plus or Br minus to start. I'm producing 1 mole of S of Ag plus and 1 mole of S of Br minus. So at equilibrium, I have S and S of those two species. Again, S equals molar solubility. You can use X or any other letter in the alphabet for all I care if you would like to. We just use S to represent the word solubility. My KSP, 5.0 times 10 to the minus 13, is equal to Ag plus times Br minus, which is equal to S squared. So S squared, because I have S times S squared is equal to 5.0 times 10 to the minus 13, and S is equal to 7.1 times 10 to the minus 7 molar. So the molar solubility of AgBr is 7.1 times 10 to the minus 7 molar. How about this example? What is the molar solubility of PbCl2 in pure water? The KSP is 1.17 times 10 to the minus 5th. Same type of situation. PbCl2 solid, giving me Pb2 plus 2 moles of Cl minus. Ions are always aqueous. Plus S plus 2S, S and 2S. My KSP, 1.17 times 10 to the minus 5, is equal to Pb2 plus times Cl minus squared. So 1.17 times 10 to the minus 5 is equal to S times 2S squared, which is the same as saying S times 4S squared, which 1.17 times 10 to the minus 5 is the same as saying 4S cubed. Solve for S, and I get 0.0143 molar. One thing I want you to note here is the solubility here. Solubility here is actually kind of high. 0.0143 molar is actually soluble. The previous example, we saw it at 7.1 times 10 to the minus 7, much smaller. But look at your KSP values. 5.0 times 10 to the minus 13 versus 1.17 times 10 to the minus 5. So that KSP definitely correlates to how much is actually soluble, as it should, but it's just mathematically backing up what we already know. What is the molar solubility of AgBr in a 0.1 molar NaBr solution? The objective here, be able to determine the molar solubility of a substance in the presence of a common ion. So now I've got 0.1 molar NaBr in solution. What does that mean? That means I really have 0.1 molar Na plus and 0.1 molar Br minus in solution. We just determined the molar solubility for silver bromide in the previous, two slides ago. We determined to be 7.1 times 10 to the minus 7th molar. So just this was 7.1 times 10 to the minus 7 molar without NaBr present. This example deals with the common ion effect. I've got AgBr dissociating into Ag plus and Br minus. I don't have any Ag plus to start, but I do have 0.1 molar Br minus from the NaBr. Plus S, there's 1 mole of each, it's 1 to 1 mole ratio, S and 0.10 plus S. Set up your KSP expression. KSP is 5.0 times 10 to the minus 13 equals the concentration of Ag plus times the concentration of Br minus. Plug in my values from equilibrium. 5.0 times 10 to the minus 13 is equal to S times 0.10 plus S. We're going to assume this S is really small and goes to 0. We're going to ignore it. So it does simplify our math. We have 5.0 times 10 to the minus 13 is equal to 0.10 S. S is equal to 5.0 times 10 to the minus 12 molar. So previously, we had 7.1 times 10 to the minus 7th molar. Now I've got 5.0 times 10 to the minus 12 molar. That's because of the presence of a common ion. It's the common ion effect. It's repressing the dissociation of the silver bromide. Less silver bromide will actually dissociate or ionize because I already have a bunch of bromide in solution from the sodium bromide. Le Chatelier's principle in effect. Let's work another example like that. What is the molar solubility of PbCl2 in a 0.1 molar NaCl solution? We don't have any Pb2 plus to start, but we do have 0.1 molar NaCl, which creates 0.1 molar Cl ions at the start. Plus S, plus 2S, S, and 0.10 plus 2S. Your KSP expression, Pb2 plus times Cl minus squared equals 1.17 times 10 to the minus 5. Plug in the values we know. We have S times 0.10 plus 2S equals 1.17 times 10 to the minus 5. We assume this is really, really small comparative to the others. So we now have, but this quantity is, this box is squared. So the 0.1 is squared. So we have S times 0.1 quantity squared is equal to 1.17 times 10 to the minus 5. S is equal to 0.00117 molar. Or we could write this as 1.17 times 10 to the minus third molar. When we did, so that's in the presence of sodium chloride. We did this a few minutes ago. We had PbCl2 by itself, and we found it to be 0.0143 molar, or 1.43 times 10 to the minus 2 molar. So we can definitely see again the effect of that ion repressing the overall solubility of the solution. What is the molar solubility of aluminum hydroxide in water? The KSP for this is really, really small. So we've got aluminum hydroxide. That should be a 3. And this is dissociating into Al3 plus ions and 3 moles of hydroxide ions. We don't have any aluminum to start. Aluminum ions, I mean, so we can say plus S and S. But here's the trick, hydroxide. Water naturally has a hydronium concentration equal to hydroxide concentration, and they are each equal to 10 to the minus 7th molar. So we actually do have 10 to the minus 7th molar hydroxide, which often doesn't matter, except this KSP is incredibly small. So it may matter. Plus 3S, and we get 3S plus 10 to the minus 7th. We have 2 different approximations we can do here. So let's see, our KSP expression is Al3 plus times OH minus cubed is equal to 3 times 10 to the minus 34. And so S, if we substitute in our values, S times 3S plus 10 to the minus 7th cubed is equal to 3 times 10 to the minus 34. We have 2 possible approximations. And we need to check both. First, we can assume 10 to the minus 7 is a lot smaller than 3S. If we do that, we have S times 3S cubed equals 3 times 10 to the minus 34. 3S cubed is the same as 27S cubed times S is 27S to the 4th. And if we solve for S, this gives me 1.8 times 10 to the minus 9. Check your assumption. Nope, it does not work. 3S is not greater than 10 to the minus 7. Which means I cannot use that approximation. The second approximation we can do is assume that 3s is a lot smaller than 10 to the minus 7. In that case, we would have s times 10 to the minus 7 cubed equals 3 times 10 to the minus 34. We solve for s, and we get 3 times 10 to the minus 13. I forgot the 1 in front of that, 13. That one is correct. We can assume that 3s is very small compared to 10 to the minus 7. Our solubility is really small. How did I know to look for that? Truthfully, the KSP is really, really small. The fact that the KSP is so small means that water's probably going to interfere a little bit. Also, just the fact that there's hydroxide in solution allows me to have a common ion effect, so you need to pay attention that water can also be your common ion. And it comes with practice, just lots of practice. But if you see something like hydroxide like this and a really small KSP, there's a good chance that the water is going to compete as a common ion.